last couple of days of the meeting. Let's go. So hello everyone, my name is Walter, if you don't know me. And I will be talking about something that come up in the first week, mostly that it was like, and during the old talks, a lot of people mentioned about these PNG or this FNL or these FNL constraints. And I'm going to talk about exactly about that. So how to extract primordial locality from Galaxy services. So I wanted to start my presentation with this picture. So recent Galaxy services have been really successful now in zooming out different regions of the universe and looking more and more structures. And this implies that the extracting information of cosmological information from these now galaxy catalogs is becoming really, really difficult. So people usually use something that is known as a summary statistic in case, or if you want to use like field level inference, it will be a little bit more difficult, but in the standard scenario, people use summary statistics to collect or to extract the cosmological information from the statistical distribution of galaxies. So one in particular summary statistic is known as a two-point correlation function. This video was shown before also by Enrique. And the idea of the two-point correlation function is that you can summarize the distribution of galaxies by counting pairs of galaxies. And by this pair counting will give you a function that summarizes the statistical information as a function of the separation between the two objects. So you can see you have pairs here. You start to compute in some histogram. And then from the histogram, you extract the two-point correlation function. So the two-point correlation functions have been used before for different galaxy surveys, both photometrics and spectroscopics, to extract different properties of the universe, such as the expansion rate, the growth of extractor, the composition, omega matter, et cetera, But one pending task is that what can the two-point correlation function from these galaxy surveys can tell us about the initial conditions of the universe? This is a different question in the other. So what do I mean when I talk about initial conditions? I will be talking mostly about cosmic inflation. So cosmic inflation is an epoch of exponential expansion during the early universe, driven by the dynamics of some scalar fields or scalar field. And the idea is that fluctuations of these quantum fields or fluctuations of deep fields can become quantum. And then this is a way to generate the initial conditions of the universe in the way of describing these curvature perturbations. So parameterized by this curvature perturbation. And then you can compute two-point correlation functions or higher order statistics from these initial conditions or these curvature perturbations. And then you can set its statistical properties for the primordial fluctuations of whatever matter content that you're using. So for example, you can compute the two-point correlation function and you obtain something that is known as the primordial power spectrum, which is something that you put in your CAM or class codes as AS and S. So you are essentially defining this part of the initial conditions. And the idea is that you will start from these curvature perturbations, then these curvature perturbations will make halos of that matter. And then you can connect these dark matter halos to galaxy over densities by relating that matter to galaxies using the linear bias or higher order bias, depending on the level of theory that you are talking about. I want to also mention that I will be referring mostly to the linear regime during this presentation. So essentially, this galaxy bias will be labeled as the linear galaxy. And the idea then is the same. So you have the primordial power spectrum. From the primordial power spectrum, you compute the matter power spectrum. And then you relate this with the galaxy bias, and then you obtain the galaxy power spectrum. That's a little bit the roadmap for these things. And here you can see a picture of the EBOS and BOS LRG's power spectrum, just as a reference that you can do it. So which property that we want to extract from the initial conditions is basically known as primordial Gaussianity. So as mentioned before, you have cosmic inflation. Cosmic inflation relates to the curvature perturbations, and then you can compute two-point correlation functions. But one interesting property that cosmic inflation has is that most of the information is captured in these two-point correlation functions, which implies that these curvature perturbations follow a close to Gaussian distribution. But if you have more fancy model of cosmic inflation, you can start to constructing higher order correlation functions from these curvature fields. And for example, if you compute the three-point correlation function, which is known as the bias spectrum, you can extract you can try to measure this FNL parameter, which is the amplitude of this bias spectrum. And by measuring this FNL parameter, you can essentially try to disentangle between different models of cosmic inflation. So here we'll be focusing just on the simplest case. You have all the types of non-Gaussianity, but I think Gonzalo would cover maybe that. So one can ask ourselves then is that if you can compute triple correlation function of these primordial initial conditions, can we try to measure this FNL by computing higher order statistics from the galaxies over densities? That is, computing higher order correlations from the distribution of galaxies to measure this FNL. And it can be done, but it's really difficult. So as mentioned before, even though if you start from primordial initial conditions, no Gaussian, the evolution of the structures will also imprint non-Gaussianity to the distribution. So in general, it's really difficult to disentangle between non-Gaussianity coming from a primordial origin or non-Gaussianity due to the evolution of the universe. This can be done, but it's really difficult. So I will focus mostly on another way to measure this FNL local parameter, which is something known as a scale-dependent galaxy bias. So again, as mentioned before, just have the curvature perturbations. These curvature perturbations relate to that matter of densities. And in order to relate these matter of densities to actual galaxies, you have to introduce a galaxy bias. And in the linear regime, this is just a constant. But now if you have non-Gaussianity of the local type parameterized by this expression from here, essentially this linear relation given by a constant changes now introducing this FNL parameter and some scale 1 over k squared dependence to this galaxy bias. So how this happened or why this happened? Essentially because FNL gives you a way to couple short wavelength fluctuations with long wavelength fluctuations. And these long wavelength fluctuations will modulate the small scale ones which relate to the galaxy bias, introducing these now scale dependent to the galaxy bias. So now how this galaxy bias affects the distribution of matter or galaxy in a particular case. You can see it here, for example, for the power spectrum, where in blue you have the matter power spectrum for FNL equals 0. But now if you increase the value of this non-Gaussianity parameter, you start to have these features here. For example, the orange curve here, if you have FNL 100, or the green one if you have FNL minus 100. Interestingly, since the two-point correlation function is the Fourier counterpart of this power spectrum, you can also transfer the same effect to the two-point correlation function, as you can see here. And in blue, you have the two-point correlation function without any effect of FNL. And then in orange or green, you have different values, FNL 100 and minus 100. So the interesting thing is that you can use this kind of tilt or on the two-point correlation function to measure these FNL parameters. And this is something that has been done before. I think I don't have the daily plot with the test results yet. But the idea is that this whole program is trying to compete against the constraints coming from CMB. So for example, you can see in orange, the different constraints of FNL coming from CMB experiments, and you have this one which is from Planck 18. And then in blue, you start to see how the constraints of FNL have been evolving through the years using this scale-dependent bias method. Yes?
Those plots that you shown in the previous slide,
yes.
Are they all for this k-squared, the inverse squared
yes.
relation?
Yes, I'm only considering this kind of. Yes.
And principle you both also consider other dependencies.
Right. So it could be possible that if you have other type of non-Gaussianity, the shape of this galaxy bias will change. So you will not have, for example, this 1 over k squared. So you will have a little bit more effects in different scales. So it can change depending on the type of non-Gaussianity.
This kind of bias, k-dependence bias, it's degenerate with modified gravity. Can you disentangle this kind of effect from primordial non-Gaussianity with modified gravity? That probably should induce a scale events.
You're only going to get the scale-dependent bias in modified gravity if it violates the equivalence principle.
But you could. Modified gravity, you can have this kind.
But there's probably some sort of a screening where it becomes relevant, doesn't become relevant. So you have some scale there that gates what this happens. And I think that's not the case. Okay. That would be my guess at least, right? So we've like tested.
I'm not completely aware of it.
It is also the scale, like, use super big scales, you can modify, but at least the one that I would expect, like the bar or whatever, the scale would be the cluster, but screening would be, I don't know.
It's possible. Yeah, like massive neutrinos do the same thing technically. They suppress the power spectrum by 1/k squared, but it's at the scale of neutrino free streaming. So this happens at much smaller scales. So that's this like 1/k squared. So you get these things from.
You do could have difference, for example, for when you're trying to consider relativistic effects, and then you can have like some scale dependent on large scales. But we will not be considering this as a fiducial case right now. So yeah. So then one interesting thing that you're going to start to notice here is that, well, the name of the game here is trying to improve the constraints and to get constraints much better than the one that Planck already has. So Planck has around an error bar of around 5. But the interesting thing is that if you already have like a detection of order 1 of FNL, this already implies beyond standard scenarios of inflation in the simplest case. So this will imply beyond single field slow roll inflation. But if you have like a value of FNL close to 0, then you will tell essentially that you will have single field in the simple case. This is a little bit the claim. So essentially trying to measure this FNL parameter is basically a smoking gun to differentiate between single field and beyond standard inflation scenarios. One interesting thing here also that you can see is that most of the constraints are coming from spectroscopic surveys, except maybe this SESS one, which is a photometric sample. But it's interesting that there is a result that's saying or arguing that photometric survey could play a big role in breaking this sigma FNL equals to 1 barrier, mostly because by being photometric, you can just grab a large number of objects, and this is claimed that it could improve the constraints on the FNL. So I will spend most of my talk talking about my photometric survey of interest, which is the dark energy survey. And I will just go really briefly about some things because this haven't been discussed by Anna before, so I will just skip some parts.
One question. You said that
Yes.
because you have a large number of objects, but it wouldn't be more like you have a huge footprint.
I think it's
the most important footprint.
Right. I think I will show that it's a combination of both. So you will have large area and large density per area. So it will be like. But the main principle is that it's bigger and larger and more things. Is the constraint that they made in this paper. Of course, this is up to see. It will depend on survey properties. So we will have to test against these. So just briefly, the dark energy survey is around 5,000 square degrees. It's a photometric survey in 4 color bands, implying that instead of knowing the redshift exactly from each galaxy, you use these bands to estimate, for example, from these points, the redshift of a galaxy, implying that each galaxy will have some uncertainties in the determination of redshift. And you can see here the footprint covered for the ES for different years, and has been taking data for 6 years, so this was already mentioned. And as I mentioned before, you have some uncertainty in the redshift. So what we do is to split the whole galaxy sample in different redshift beams in order to, well, depending on just because we don't have the accuracy and redshift. And the important thing is that curve selections in the galaxy sample can be used to select different galaxy samples. So for example, you can start to select galaxies by different colors and different properties in the different bands. And this has been done before to define the behavior sample, for example, or the McLean galaxy sample, which is a selection for optimized for galaxy-galaxy lensing. So this is the main idea, or the main property that the ES has. So the big question is, can we use the dark energy survey to measure this FNL parameter? And with that, I'm part of this collaboration of different people. So here we have also Anna and different projects, and Hugo. I will be talking mostly about the angular correlation function methodology, which is trying to measure primordial ascending from the angular correlation function. And then I will also briefly mention some sample optimization project that we are currently working with Anna. And this is the main idea of the first part of the angular correlation function. So the idea is that we will define and validate the pipeline to using the angular correlation function for measuring primordial density from the dark energy survey. Then I will briefly define what is the integral constraint and the impact of the integral constraint, which is something like kind of modern now. This is already implementing it, so it's fine. And then I will just briefly mention some robustness tests we use for the pipeline to define a little bit the consistency of the pipeline. Sorry. So how do we measure FNL? So again, I showed you before that the two correlation function can be used to measure this FNL parameter. So this is kind of similar. So instead of having a three-dimensional correlation function as for the two correlation function, the angular correlation function is exactly the same, but instead it's a it's not exactly the same. It's a two-dimensional projection of the two correlation function, where you project this set dimension by using the N of C distribution, which are the redshift distribution that I showed you before. And interestingly enough, you can see that the angular correlation function is also affected by this. You can see similarly on the two correlation function, you can see how the angular correlation function changes for different values of FNL. So in order to validate our methods, then now that we define the angular correlation function, we will have two sets of simulations. One of them are the ICTP-SAIFR, which are around 2,000 simulations, are quasi-embodied simulations. I don't know the detail why it's quasi, but the main property is that this has FNL0 as initial condition. They cover an area similar as the one from DES. And they also have all the properties from the DES sample. So from the DES Y3 VAO sample. So they cover the same redshift. They are split also into 5 redshift beams. And they also have the same angular distribution. So we will use these simulations to essentially validate our pipeline and try to see whether we can recover FNL0. And then we have also the Goliath PNG mocks, which are simulations that cover a little bit less area, but they have the particular property that they have FNL minus 100 and 100 as initial condition. So in here you can see in the plot difference of the area coverage from the simulations from the SQL simulations. And in green you can see the Goliath PNG simulation. So this will be used to validate essentially the pipeline. So what is the main idea now? The things that I'm going to show you is that first I'm going to describe what is the integral constraint and the importance of it. Then I will just briefly mention the validation methods that we use for the pipeline. And then I will not finish, but then I have something else. But I will almost finish with the galaxy sample optimization for this measuring primordial density. So let me start first with the integral constraint. So what is the integral constraint in one slide? It's basically that for limited window surveys, you essentially have the condition that the power spectrum, when you go to really large scales, has to go to 0 because you have some window limitations in your survey. And this translates on a condition to the two-point correlation function, which is that the integration over the whole survey footprint of the two-point correlation function has to go to 0. Why this integral constraint condition is important? Basically, because in presence of primordial Gaussianity, this integral constraint condition might not hold. For example, here you have the power spectrum at large scales where you have some NS equal 1. And you can see if you go to 0, the power spectrum, the max power spectrum will just go to 0. But if you have now the non-Gaussian case, in case of non-Gaussianity, you have this extra 1/k² dependence, which will essentially drive you to a divergence at large scales for the galaxy power spectrum. Yes.
Don't you have to be very careful with like gauge considerations and GR effects and making sure that your observables are properly defined when taking this limit?
Yes.
Like naively, this is naively true, but in practice, like just depending on the gauge you use to calculate CAM, your answer is going to be different, and you have to do light cone propagation and all that to make sure that these two cancel out.
I completely agree. So, and here this is a little bit more schematic, but I think when you have this condition in a more smaller survey that doesn't cover the whole case, then the problem becomes a little bit less important at the small scale. So we have a small area, it will not notice too much. I mean, but I do agree that these are important things. So yeah. Yes.
This could also be non-zero even in a Gaussian universe, right? Because, for example, if your Gaussian is not centered around zero, then this interval would not be zero, right?
If my Gaussian
Yeah,
fluctuations.
because I suppose that this interval is zero because on average you have as much as correlation as anti-correlation.
Right.
Because it's a Gaussian field around zero. So this
Right.
is zero. But if it's not centered on zero, for example, in a universe that has some huge monopole,
Right.
or due to some huge void, I don't know, then this not necessarily needs to be zero, even though it could be Gaussian.
Right, yes, I agree. But the main difference there would be also we would have to shift the integral cosine condition to not be zero, but be the background thing that you would have for a full unwindowed universe, right?
Right.
So we can just shift the condition to whatever the monopole or the background peak fluctuation is put it on like a background level. Yes, but I'm here considering that Gaussian case centered at zero. So
Sorry,
Yes.
can you go back one slide? Can you comment about this expression on the right of power spectrum voting as one of the key the four?
yes,
Doesn't it spoil the linear power spectrum? Because if k goes to zero, this goes up, and then the linear power spectrum is not. Your fields are not linear anymore. Your perturbations are huge, right?
but here, if you go to larger scales to a small case, you are going deep in the linear regime. Right?
Yeah, but then the power spectrum goes up, increases, right? Because if k goes to zero, p power spectrum goes to infinity. So I'm saying that
Yes,
if you go arbitrarily close to zero, the linear power spectrum goes arbitrarily, increases arbitrarily to higher values, then this spoils linear perturbation theory.
at large scales, you mean?
At small, yes, at large scales.
If you have FNL.
Yeah,
But it doesn't use not reason, no?
yes,
Yeah, but then this spoils linear perturbation theory.
right. That's why I mentioned that it is a problem, right?
Ah, okay.
Yes.
So
So that's why we need to impose this integral constraint condition. That is why we need to enforce a little bit, depending on the survey size, this condition to hold, because you have these particular divergences. Yes. Sorry about the issue. So then you can try to impose the same condition now in the algorithm correlation function as you showed you before. You can have this integral over the mass of the two-point correlation function, which in particular case, you can simplify this integration over the whole superproof survey footprint to, instead of integrating over the whole survey footprint, you can just use this random pairs, which is also a way to determine the volume of a survey. So this random pairs is it's a pair counting of a random simulation that has the same angular distribution of the survey that you want to use.
But sorry, going back to the question before I leave.
Yeah.
This is divergence, a gauge divergence? It's not gauge divergence, right?
The divergence here was just a simplistic case just to
I
highlight.
know, but it's a gauge divergence. It's not gauge invariant. Don't have any gauge invariant divergence. Why do you?
Yeah, I think if you treat it very carefully, because your survey has a finite volume, there's always an IR cutoff to your calculations.
Yes.
There's no actual gauge divergences, but you still have to be careful to make sure that.
On the data, there will be no divergence, maybe because of finite volume.
Yeah.
But you have to match your calculations to always, to the survey that you, like, when you have,
This cannot be
everything on the
survey
light
cutoff.
cone, right? So I think you have to be very tricky about doing this when you go to very large volumes.
Yeah. From the theoretical side, we are actually not considering like these really large scales. So we are considering large scales enough where the gauge, we don't see gauge effects in practice, for example, from the theory part. So
So seeing they are super volume for you. Yeah. Super covariance. Yeah,
yes, I
beyond
would say
the
so,
larger
yeah.
scale, as you can see. That's what you said.
Yeah, well, we are limited, so we will take some simplistic choice about which is this largest scale that we were allowed to go in order to avoid a little bit the discussion of gauge effects that you can have at really large scales. So our model will be in the linear regime, going to a large enough scales that we don't see these gauge effects.
So this is just done because it's not easy to model, because my feeling it seems that one of the, in the place where you're seeing most of these effects are at the biggest scales, no?
Right.
But then it's true that there might be some age considerations for how you
Yes.
measure that. So is it something that is just practical for like survey, I don't know, like masks of the survey that are also like difficult to model? Or is it because it's difficult to model at the mathematical or GR effect?
I think it's a little bit of both. So if you try to go to a really, really large scales from the modeling part, you always have some effect that could be degenerate with this effect. So we try to simplify it a little bit our model in that sense. But also when we try to measure, or when we go to large scales from a survey perspective, we don't go to the largest scale possible, because then even then you will have a lot of error bars just to cosmic variance. So we try to be not the largest scales as possible. So we still constrain ourselves to a smallest scales.
Subfluorized.
Yes, subfluorized. So then we can impose this integral constraint condition to this angular correlation function. The particular condition for the angular correlation function has this particular shape coming from this condition here. But the important part is what happens when you include it to your simulations, right? So in here, you can see the angular correlation function measured for the simulation that had FNL as initial condition. And in blue, you see the measurement from the simulations. In green, you see the theory model of this scale-dependent bias with FNL 100 without considering any integral constraint condition. And in orange, you can see how the theory model changes when you're including this integral constraint. So I think we can all agree that at least in this particular case with FNL 100, you can include this integral constraint, and it has like a suggestion that it could be really important when you try to measure FNL. So how do we see these in the measurement over the Goliath simulations? This is a similar case, but now measuring FNL. In the contours, you can see in green what is the measurement of FNL for the particular case of no including the integral constraint. And you can see now how the constraints shift when you include this integral constraint. Basically recommend the fiducial values of the simulation for both cases of FNL 100, in here in purple, and FNL minus 100. So essentially, in here, we're showing that this integral constraint is essential to avoid biased values of FNL, where we practically recover the fiducial values of the simulation within 1 sigma. So now, with this argument that is important, so now we can move to a more realistic scenario, which is the case of the dark energy survey. So again, we want to use, as we already validated the effect of the integral constraint, we want to use the angular correlation function, including this integral constraint, and then we want to validate the method in a realistic DES-like scenario. And we also want to forecast the effect of primordial insanity for the dark energy survey using the ICTP simulations. So in here, you can see essentially the same plot for the Goliath PNG mouse, where in blue you see the angular correlation function measured for the ICTP simulations. In green, you see the theory model with FNL equals 0 without any integral constraint condition. And in orange, you see again FNL equals 0 with the integral constraint condition. And we test our model against different scenarios or properties that we could have. For example, the importance of the integral constraint. We also tested which best fit could be possible to use for this FNL parameter. We also tested the importance of trying to include some extra theory model on this BAO damping. We also tested against trying to select different scale choices. So from which, basically from which angular scale we will be measuring this FNL parameter. And we also tested some robustness against changes in the covariance. So this is a little bit of summary of the things that we tested. And I will include 3 of the main results that we got from that. One of them is the importance of the integral constraint. So you can see that even for the case of FNL0, of simulations that had FNL0 in the case for the case of ICTP, we see that the integral constraint actually improves the accuracy of the simulation. So here you can see in orange how the integral constraint, how FNL looks without the integral constraint. But if you include it, you get back this blue line, which is much centered in FNL0. So you can see a deviation of FNL about 7 if we don't include this integral constraint. And then we also test this model when including BAO damping in the modeling. More important here, so the idea of this BAO damping is that you can try to model this using nonlinear theory, the damping of the BAO peak. And here basically show that there is no big difference in including this extra modeling part. And more importantly, that we show is that going to larger scales basically improves the precision on this FNL parameter. You can see that, for example, if we measure these, if we try to measure this FNL parameter from 1 to 5 degrees, we have an error of around 30 something. But then if you try to measure this FNL parameter of order down to 20 degrees, then we can see that we improve the constraint up to 31. So the main idea here, as it is expected, if you go to larger and larger angular separation, this improves the constraints on FNL. And we also show that it was robust against different kinds of variances, both theoretical or coming from the simulations. So now the main conclusion from this part was that the angular correlation function with primordial uncertainty and including this integral constraint can be used to measure FNL within the dark energy survey collaboration, where we forecast an error of FNL of around 31 when using the Y3 BAO sample. But this gives us a remaining question is that what about if we use different galaxy samples? And this is the part that we'll be talking now. So as I mentioned before, you can use different galaxy samples, or you can take the data from the ES and select different galaxy samples. And then you can try to optimize your galaxy sample to lower the errors on this FNL parameter. And the main thing that we'll be using is based on this color selection that's known as the McLean color selection, where you have this particular selection of the I-band that depends on both A and B and the photometric relationship of the sample. This particular selection allows you to select a higher number density of objects at high redshift. And the idea is that, well, we can try to move both A and B from the selection of the galaxy sample and try to see how this changes the error bars for FNL. So in here, you can see the main results from this part. So we use basically a theory data vector forecast for each of the combinations from changing A and B using Y6 DES data. And here you can see basically how the constraint from FNL changes for different galaxy samples. So in here, in the first point, we have the Y3 BAO galaxy sample. Then in the second point, we have the Y3 McLean fiducial galaxy sample. And then in the other points, we have how the constraint changes from selecting different values of A and B in the selection. So when it is, no. Okay. So something interesting that we see here is this big jump from the constraint from one part to the other, which we found to be a 56% improvement just by changing the galaxy sample. Also, there are some different properties here. So in here, we're using, instead of Y3, we're using Y6. So we have more number of galaxies. Another interesting thing, yes.
Do you know how much it grows due to the having more galaxies that have been in Y6 with respect to the new cuts?
From the new cuts,
Like
from
the
new
new
sample.
galaxy selection with respect to just like having more.
So yes, I have it somewhere, but I think one conclusion that we got here is that the change in the numbers between different samples was not that much. One different thing, so one thing that we found that it was like the biggest impact is that the Y3 McLean fiducial sample goes to redshift 1.1, I think. And for the Y6, we're actually pushing a little bit more, so we're adding an extra RGB into our sample, implying basically that the biggest difference is going to higher redshift. So the biggest way to improve the constraints on FNL is trying to select a galaxy sample that goes to higher and higher redshifts. even though that the redshift accuracy might not be the best. But this is on the work, because we still have to work with these kind of things. And oh yeah, that was the last point that I wanted to see from this part.
What's the main difference between the GR3 video sample and the?
What?
What is the main difference between the GR3 video sample and the macro? Because that seems to be the largest.
Right, that's a good question. So I think the main difference between this one is based on a core selection of LRGs. So I think it's an improved version of LRG selection with some exactly quality processing. And the McLean is basically just grabbing almost everything. So I believe that this big jump could be from because of the number density changes.
The white video has also a magnitude cut that depends on redshift, like McLean, but it's a different and slow ultra magnitude cut. And then additionally it has a color cut to try to select the galaxies. So it has less normal, yeah, actually it's less normal, and also the redshift different. So white video starts at 0.6
Right.
until 1.1, and McLean goes starts at a lower redshift.
Do we understand it like our characterization of systematics would hold for these new samples at 20 degrees separation? Or just in theory, this would work, but we have no idea if these samples can be characterized well enough at these scales.
You're going to a difficult question.
Sorry.
Yeah, no, it's fine. It's fine. So the honest answer is that we don't actually know because we haven't worked on that.
Mhm.
We're basically waiting for the systematic people to be more free beside the key projects from the ES to help us to disentangle or whether it's possible to go to large scales and what's the impact of systematic at those really large scales. So this is under study. So for this particular ES case, I'm not be prepared.
Just because I'm thinking of like, you know, in DESI, it was, if you did a sort of twiddle estimate, the like ELG cross CMB lensing correlation will have the highest signal to noise for FNL by far, basically. And then it turns out that the systematics for the ELG imaging were so extreme that they just were not able to really get any constraints out. There's a
Right.
paper by Tender Karim about this, which is like they change, for example, their dust reddening law for their maps. And it shifts their constraints around by like more than 1 sigma. And you know, that's DESI, which is really high quality data.
Yes.
But I
So-
would say that ELGs have more systematics.
That's also true. That's true, but I mean, here you're, but you know, I think, yeah, I was.
But it's yeah, this is why it's still not done yet, this analysis of the lake, because it's not trivial.
Yes.
But yeah.
I also, so for like those very high red seals, I know like you mentioned like the risk determination is not great. But I don't have the intuition right now to whether that affects more than usual to the very large scales that you want to probe here. Like having poor risk determination or not, like translating the DNDC. Is
Right.
it like, does it affect more large scales than it does at small scales? It's the same. This is going to be very problematic for this.
I think this is something that we haven't explored yet, but
But doesn't affect particularly the largest scales. Affect more. It's true that extending to higher density, it will be more challenging to validate than higher density. So it might be that those higher density systems which might have more problematic. But and that's where you have more
yeah. Yeah, they were not really problematic enough for others.
Yeah,
So
that's
it's
why
like
that's
it's-
why I was asking.
Yes, in this particular case, it's still pending work. We are still have to review exactly all the things that you were actually saying, so systematic effects and everything.
But do you have an idea of which systematic would be more important?
Yeah, most important one is observational systematics, which I guess what everyone was referring to, that is correlated with a number density. So, and that is more important high density typically as well. So it changes an at large scale. Basically, you have more amplitude of the correlation function due to these correlations with observing conditions.
Man.
Yes, and that is very similar to the impact of the net. So
Yeah.
the point is that all these methods, there are multiple methods for correcting for this, but they are not perfect because to validate them, for example, you use simulations in which you infuse some systematics, but what if there are some systematics that you don't know or the methods might overcorrect and then they reduce, they remove those sort of history.
Right.
Why is this more of a problem for high redshift? Yeah, that's typical. I mean, I guess you go deeper, like you might have more analytics. Yeah. For the right magnitudes, it's already covered way up.
Right. So good that we're talking about that. Yes.
I know that you were in like consider them for this study, I guess, because of the scale cuts, although the correlation was very big, so still how to find the scale cuts there, but like, have you thought about like how to select the sample to also minimize the impact of the relativistic effects of the rest space distortion that may mimic FNL, or that's like going too much in detail and like you lose more things because of the euros, like.
Right. As you said, we haven't tested. I think how it's tested, but it's something that maybe we're referring to. This particular modeling or this particular forecast are including also virtual space sorting, but we are not seeing the deposit. We are not assigning the positive genesis with direct space sorting.
So it's included relativistic resonance space distortion.
No.
The standard.
Standard. We are not considering relativistic effects. But it's good that someone mentioned the case of DESI, because I had a couple of slides prepared for that. So that's why we had already the validated pipeline of using the angular correlation function for measure this FNL. We just wanted to explore and play a little bit to try to test this with the photometric sample coming from DESI, from this result that came from Mary a couple of months ago, where he actually measured this FNL parameter from the DESI photometric sample, which is essentially covering this whole area here, and a redshift range from 0.2 and 1.3. But the measurements that he did in his paper were based on the angular power spectrum. So our idea was that maybe we can use this angular correlation function and just to double check that we got consistency between the results that he got from his data sample, and he basically just to double check that we recovered the same. So we will be using essentially all the part of the pipeline that Mary already did. So we will be including the same galaxy sample, which are based on photometric MRGs. We'll be using the same systematic weights that he did and he prepared. So in here you can see how this on one particular map of some systematic weights, how they do. Just how it is. And then we will use this weight to decontaminate the sample. We will have this density field sample that we have here. And then from this map, we'll compute the angular correlation function and try to see whether we can, and then we will measure FNL from this map. So here you can see a little bit of the properties of the photometric DESI sample when you have around an area of 15,000 square degrees, around 12 million galaxies, and a number density of 0.2. So in here, you can see, as Nick also pointed out, so the photometric DESI part is kind of messy. So in here you can see the constraints from Mendy's paper using different decontamination of number maps from the decontamination. And in green, you can see basically why the decontamination systematic is important for FNL, because essentially if you don't decontaminate your galaxy sample, then you're having a value for FNL of around 100 or something. But also more interestingly, if you decontaminate using different methods or including different maps, the constraints on FNL change a lot from these different color curves here, as you can see. So this, well, from the part of our project is that we basically recover almost the same effect that Mehdi was seeing in his pipeline with a completely independent pipeline. So we found that the results are compatible when using the angular correlation function. But more interestingly, you can see actually that these different decontamination procedures introducing an error of FNL of around 10. So you are already having some deviations imprinted in the decontamination from this FNL parameter, which could be worrisome for future surveys, such as LSST. So in here, we have the forecast of LSST-Y1 using the angular correlation function, essentially the same timeline that we already validated for the ES. And in here, you can see, well, I have here the whole area coverage of the footprint. I'm not really sure who made this map, but someone shared it to me. It's actually labeled, like, I think the file is called mask for Paul. So Paul is someone that needed it, so I'm using the same mask. And in here, the idea.
Forecast. So it's Paul.
Right, I Paul Rodriguez. But who made it? Who made the mask? It's around. Okay.
Some friend of his.
Okay. Yeah. So then the forecast here is based on the year 1 SRD cosmology. The idea again is that the whole sample is split. We will be using the length sample, so it's split in 5 redshift beams. For this particular case, we are covering a similar area of DESI imaging, which is around 15 square degrees. And we will be using the same validating methods as before. So you can see here in the plot how the constraints of FNL look in comparison with the DSY6 constraints, where in red, you have the constraints on FNL without, where it's a constraint on FNL when leaving the galaxy bias as a free parameter. So as I showed you before, I think I didn't mention it, but FNL is highly degenerate with the galaxy bias, with the linear galaxy bias. So people usually try to see whether, so when people report the constraints on FNL, they usually report it by leaving the linear galaxy bias as a free parameter. Which is the red curve in here for the particular case of the ES, desk. And you have an error, a forecast error of around 9. And then if you try to use a fixed bias, you put the constraints of around 6, which is already competitive with DESI year 1. And I think the forecast for DESI year 5 is around also the same similar bias. So this will be actually an interesting case for LSST that only using year 1 data, you can already have this improvement in the constraints. So with that, I'm finishing. So I already mentioned to you the importance of the integral constraint. I presented some methods of validation for the dark energy survey. And I also briefly mentioned some how to optimize this galaxy sample for the metronym of primordial non-gaussianity. So I think I'm just going to leave you with this final plot, where you can see again the evolution of the constraint that I showed you in the first slide, and then you have all the preliminary work that's today here. So thank you.
I feel like.
But you asked João. João is the person.
Charge not there.
You have to ask João because
Yeah.
I control this with the computer.
Was there, I have to ask.
Yeah, but you can wait a few minutes because I don't know if this is working.
Anyway, question for.
Yeah, I was freezing, so it's that's why I have to move.
You were freezing.
Yes.
You're always freezing.
So my question is, how much does it depend on this B1, B5 relation?
I don't know. I didn't mention it. So this B5 relation is, I don't know if you mentioned it in the galaxy bias discussion or if it happened or. So just to have everyone in the same picture. You can either have the linear galaxy bias here, or you can